So I want to welcome everybody to this quick webinar. We are fortunate to have Sophie Nowicki speaking today about why now is perfect time to work on ice sheet and sea level. She's a professor at the University of Buffalo in the Department of Geology and the Renew Institute, and also one of the co-chairs of the ice sheet model and comparison group with CLIC. So thank you so much. We're really excited about your talk.
Well, thanks for inviting me. And when you asked me for a title, I didn't know what to think, but I could see that there was a lot of advertisement on Cryolist about summer schools that I kept on passing along to my students. And I was like, oh my gosh, I wish I was just starting right now. And so that came the title. And then I was like, oh my gosh, I have to follow up with this. So hopefully I will deliver my thoughts about why I really, really believe that right now is the perfect time to work on ice sheet and sea level. And it's a very perfect time to join the field if you've never done that. And so that's going to be the topic of my presentation, how things have evolved since I started and where I think the big pictures are. So if you don't know me, I'm an ice sheet modeler. I tend to think on the timescales over 100 years. This is really motivated because in the picture that you see, you have a picture of my grandmother and my kids. We are about to blow, there's a special candle. You can see the numbers, it's 105. So she's about to turn 105. So my kids are super excited. She's also super excited because she's always dreamed to have a beautifully decorated cake. She had to wait that long. So anyway, it's a long story. But the point about this photo is that in that picture, there's 100 years difference because my kids are roughly age 5 at that time. So for me, 100 years times frame is something that I can really think and I can really understand. And I hopefully, maybe my kids will face that. Now, I've been involved in those 100-year time-years projections in terms of ISMIP and the IPCC. And this is the next image also on that plot. It really shows that, to 2100, we are going to have rising sea levels, which means it's going to affect a lot of people. That was as plot captures. But there's also this dotted line that is the first time in IPCC history that we gave this idea that there is a deep uncertainty in ice, and that therefore the sea level numbers could become much, 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 much higher than what the models usually give. And this is also a motivation for this presentation. How are we going to get to this narrow, to that little spread, that dotted line that gives a very, very high sea level that we need to understand in order to, for general society. So, and that line is really due to, ice sheets, basically. It's the spoiler alert. Okay, so I'm going to pretend that you know nothing about ice sheets. So we'll start with, the cool thing about satellite observations is that we now know that the sea level contribution from ice sheet is increasing. But the thing is that ice sheets, they have a natural cycle with the climate system. With this beautiful plot of the Greenland ice sheet, it kind of shows the growth and the decay with seasons, right? So Greenland will grow in the winter when there is more snowfall. It will then decay in the spring and summer when there is melt and increased discharge, and there will be a cycle. And so if the ice sheet was in balance with the climate, you will have still that cycle that will go up and down with the season. Now, what's happening right now, though, is that the ice sheets are not in balance with the current climate. The climate is much warmer and has been climate change has arrived. And so you also have, in addition to that line going up and down, this decay of the Greenland ice sheet that's leading to this increase in sea level rise. And so the numbers that I cannot reflect afterwards on the other side of my graph is that if all of the Greenland ice sheet melted, or if part of Antarctica or West Antarctica melted, you would get a lot of possible sea level. So this is this question about this deep uncertainty, how much of that can actually come in a lifetime? Well, the thing is that now you know that ice sheets are very dynamic and they're losing mass and sea level accelerating. But if you think back when I started my PhD, or actually when I started my education, this was not the case. This knowledge was not there. In fact, the first 3 assessment report of the IPCC said generally that, we know everything about sea level change. There is no major dynamic response from the ice sheet that was expected during the 21st century. And the main contributor to sea level rise was due to thermal expansion and the melting of glaciers. So in the plot, I show for the 3 assessment report how much of the contribution to sea level rise would be from Greenland and Antarctica based on the IPCC reports. And so you would see that basically Greenland always contributed to, would always melt in the projections. So it would always lead to sea level rise. But in a warmer world, Antarctica could actually be below 0 in purple, right? And so it means it could grow because in a warmer world, you could have a moister atmosphere, which led to more snowfall. Okay, so in the first 3 assessment reports, this was basically the belief, and actually how much each ice would contribute to would change based on the different scenarios. And so I started my undergraduate after the second assessment report. And so during the 3rd assessment report, I was still doing my undergraduate degree. So this was the current knowledge. Ice sheets don't really matter, okay? But then something happened. We started to have satellites being launched, and this was the first type of a worldwide picture about what was going on to the ice sheets. So this is from ERS satellite, the change in elevation from 92 to 97 produced by Riga Metal. And so at that time, when it came out, I was just actually starting my undergraduate. So this is how old I am, or basically how old this image is too. But basically think about this knowledge. This was what we thought about Antarctica. It's a very boxy thing. You can see that, well, maybe there is mass being lost now that you know around Thwaites and Pine Island. Probably, yeah, this is kind of, you could guess, but maybe it's also noise, right? You really can't really tell from this kind of image. So that's why this belief that, ice sheets were kind of like this giant snow cube, happily not doing much, was valid in the IPCC report. But during that time, you also had, between the 3rd assessment report and IPCC AR4, you basically had the observational record became longer. So now I'm showing you the change in elevation from 92 to 2003 from the same satellite. Because the observational record is longer, you can really see trends in behavior. And now you can really tell in this blue line and purple line that there is something going on in Pine Island Glacier and Thwaites Glacier, and there is a signal. And so this is the assessment report, the 4th assessment report that kind of said, okay, maybe the sending of the ice sheets are really not what it should be. We know the observations are trying to show us dynamic change. But however, we also understand that our current knowledge of this effect, that what we're seeing, is too limited to really understand what the future they have, the impact in the future, or it's also too hard to kind of give this estimate of an upper bound for sea level rise. So we went from the 3 assessment reports saying we know everything about sea level and ice sheets do not matter, to a 4th assessment report saying actually we know nothing. And that's reflected when I started my PhD. So I'm now in UCL. And so now you can start seeing, the lines kind of changing and the behavior in the curves changing. Came the next assessment report, AR5, where basically the key statement is like, okay, great, we now projections are larger in AR5 than they were in AR4, mainly because of improved modeling of land ice contribution. But however, we still have many uncertainties, in particular linked to ice sheets contribution. And so really, I would summarize this as we know something, but not enough. And this is when I started my career as a civil servant at NASA Goddard Space Flight Center. And you can also see in that plot that now we are also splitting the Greenland contribution and Antarctic contribution due to the dynamic. So the part that is really linked to the ice sheet models and the response, and the other part that is basically not hashed, the solid part, which is just due to surface mass balance. Right. So what happened though for AR5 is that there was a lot of communities. There was 2 communities trying to really deliver the best level projections. There was the Sea Rise effort, which I was involved at NASA Goddard. There was a bunch of American scientists trying to develop this community effort with no funding. So it was really kind of ad hoc kind of effort. And then you had the European project called Ice2C, which was lots of money, lots of funding, doing things very, very carefully. And we'll talk about that. But basically, at the time of AR5, CRISE and Ice2C were two groups, a European group, an American group, kind of like fighting with each other, really like kind of children in a kindergarten. And this is when Click became very important. One of my friends, Eric Laro, wrote to Click and said, look, come on, this cannot happen. We can't have this for AR6. We can't have different communities fighting in terms of sea level. Find a way to make them work together. And so Click helped us get our first workshop at NASA Goddard Space Flight Center in 2014. And this is when we had those two communities together and we decided to actually work together and create ISMIP6. It was an incredible group of scientists. I'm not going to go through all that we did. A lot of what's did is in this crazy timeline. Basically, generally speaking, the arrows are deliverable when we had to publish a paper or publish something for CMIP6. Like there was very big deadlines that we had to do. Triangles were meetings that we would meet at AGU, EGUs whenever we could meet. Special red stars where we actually had money dedicated to bring all of us together in the same room, and that's not very often. So there was that at the beginning of the project in 2014, and then this picture here that was taken in 2018 in Sessenheim. In terms of solid lines, is whenever we are actually doing ice sheet numerical simulations. So we did simulations for Greenland in green. So two different types of simulations, one to look at the effect of initial state, the other one, the projections. So therefore we do the initial state at the beginning because, we cannot need to get ready, and then we do the projections towards the end. And then the dotted lines are when we have focus group trying to develop a better protocol. And so we had the red line is the protocol thinking about different type of CMIP model selections. The green line is how we do Greenland surface mass balance and ocean melting. And the blue line is how we deal with Antarctica. So a lot of people working for a very, very long time that gets this very strict deadline of having everything done, published by or submitted by the end of 2019. Otherwise, it is not on time to be considered by the IPCC AR6. Right, so this was the kind of craziness that we had to kind of deal with, and that this group of scientists managed to do. You can get more information on Nowicki, but really the key point is that this really started because of Click that kind of helped bring two communities together that otherwise would continue fighting. So what is behind the ISMIP6 projections? We have both Greenland and Antarctica. Basically, the key takeaway message is it's open to anyone who wants to join. So we have a diversity of ice sheet models that represent the current state of the art. That is basically fed by multiple future climate forcing. And it is very important to take away from that is that, we do the very rigorously model selection of the CMIP climate models, but the key takeaway is that they all project something different. And so the future of what the polar climate will be is very uncertain. And that is one of the reasons that we have this big uncertainty. Because you can see that, you have your red lines, different lines for different colors for different models. They do not always agree on where they are. So for example, the red line, which is UKSM, is not always on top of the pack. It is in general for the ocean, but not for the atmosphere. So it means that it projects warmer oceans, but not so much atmosphere. And in contrast, the blue line, the CSM line, is really, really hot in terms of the atmosphere. And surface temperature anomaly, for example. But in terms of the ocean, it really is not that much, or it depends on the region. So projection of ice sheets is going to really become a part of also this climate forcing. So, okay, so we get a diversity of ice sheet model fed by possible future climate is therefore going to lead to a very wide range of response in sea level. I try to summarize some of the key findings. In general, you see that West Antarctica is going to lose mass for most of the climate model, but not all of them. This is what my box plot kind of show. So the different colors is the response to the different climate model. And then the spread is actually due to the ice sheet dynamic. So basically the complexity that we are now facing is that each ice sheet model also is going to respond differently due to those imposed climate forcing. And that's why it's kind of a zoo. I call it as a zoo of climate model and a zoo of ice sheet models. But in general, West Antarctica is going to lose mass. East Antarctica could either gain mass or lose mass. This is kind of also unknown. And the peninsula, in general, again, is a bit unknown, but is not much less sea level because there's not much ice to lose. We did over 344 simulations. We had 13 participating ice sheet models. We used 6 CMIP5 models, 4 CMIP6 models because they were delayed, so we had to use CMIP6 models. But anyway, the point is that there's a lot of simulations by a lot of people. However, this is not enough simulations. Like 344 simulations is just not enough. Right, so then what we did is that we used emulators. And emulators is basically those what I give as a solution for those bell curves, where basically it's kind of machine learning on those selected all of the 344 simulations, how much sea level you get for a given temperature, and then you can make projections for a whole wide range of scenarios and different temperature. And this is what AR6 had to do for the IPCC, because we had different scenarios that we had to consider, and we also needed to fill the gap. So this is a new opportunity for research. It was the first time that emulators were used. Whether we use the right emulator, I don't know, but this is a cool thing to look into. So in general, in a warming world, West Antarctica is going to, there's a consistent story. It tends to lose mass always. East Antarctica in a warming world may actually gain mass. And that's why the two of them kind of cancel out a bit. There are big numbers that do cancel out. And that's why it's kind of tricky. So with all this work, if I kind of put it back into the IPCC table, and what is behind this IPCC table? Well, you have emulated Antarctica, but you also had simulations from other MIPs and more. Solar MIP is with another MIP. In terms of result, what do you get? Well, for ice sheet models, the majority of ice sheet models, which we see what we call medium confidence processes, actually, the numbers are quite similar to the previous assessment report, despite all of this crazy work. So maybe we should have not bothered, right? But at the same time, you can't, like, we didn't know, because it's actually pretty cool that, it is the first time in CMIP in IPCC history that actually Greenland and Antarctic ice sheets projection are based on an ensemble of ice sheet models. It's also the first time in IPCC history that those ensembles of models are used with improved forcing. Because remember when I was telling you at the beginning about sea rise fighting against ice to sea? Well, what sea rise did for AR5 is that we had a bunch of ice sheet models, but we kind of said, hey, to do basal melt, we're going to do 2 meters per year basal melt everywhere, and then we're going to do 20 meters per year basal melt everywhere, and then we're going to do 200 meters basal melt everywhere. Like basically, we were not tied to the climate modeling community. And so the only way we could kind of think about the way that the ice could respond in different warming scenarios was to do this kind of schematic type of experiment, which is not really okay. So a big thing for ESMEP was basically using scenarios that were consistent with the rest of the climate community. We're now using an ensemble of climate models giving forcing for an ensemble of ice sheet models. And what is pretty cool is that now this data is also available for all and other studies to kind of dig into. In terms of the high emission scenarios, the RCPs 5.5, 8.5, then again, those numbers for those medium confidence process from ESMEP and LAMEC are very similar to the previous assessment report. And what I really believe is that it's because, the ice sheet models are forced by the climate models that they're being forced. And so if the climate hasn't changed, if the projections of climate hasn't changed between different assessments, then it's kind of logical for those two to be very similar. Because remember, a majority of ESMEP 6 simulation were based on AR5. Therefore, we are naturally biased towards AR5, even though we're using ESMEP 6. Okay, but what is cool about this graph too, that is new about IPCC, is those two other plots that give much higher sea level number. And it's basically the recognition that there is uncertainty in the projections. And what does that look like? I mentioned already that there is an uncertainty due to emission scenarios. So whether you're going to have a high emission scenario the RCP 8.5, or low emission scenario, the RCP 2.5, right? So RCP 8.5 is like business as usual, and then the other one is that we try to curve. So there is an uncertainty in what we're going to do as a human. And then there is an uncertainty also due to the actual climate model that do along the same path. Like so the high emission scenarios, this was my colorful plots where there were everywhere spaghetti lines at the beginning. And then there is an uncertainty here that is linked to the ice sheet models themselves. There's basically a big spread because one ice sheet model might respond differently. So that uncertainty for the ice sheet model is due to things like how they implement basal sliding, how they do glacial static adjustment, how they do basal melt or ice bedrock interaction. So all of those are processes that maybe are still uncertain, and for me, that are really worth looking into. They're really cool. Then there is uncertainty due to insufficient data. This is the bathymetry one. Because until you know what the bedrock is beneath it, you won't know how the ice sheet is going to retreat. So until you make any progress in any of those, you will have this uncertainty and this spread in projection. Now, the biggest uncertainty is basically going to be whether, and the biggest source of deep uncertainty is whether you're going to have a collapse triggered either with the marine ice sheet instability that can be triggered by a retreat of the grounding line, and that can basically collapse anyway. Or you could have this marine ice cliff instability, which is a concept that basically, if the ice is so thick, it might collapse and retreat becomes unstable. And those are still question mark, both of them. So this is captured in the IPCC report. That's why it's quite cool. And this is what is there in this yellow line, in this red line. The Nowicki is captured. We have projections of that give us a higher number. And then SCG is expert elicitation when you ask a bunch of experts what they think. And so it's not ice sheet models, it's basically asking the community. And so you capture the fact that maybe there are processes that we still don't know. Those numbers were also guided by ISMEP6 did do some crazy experiments, like sea rise, where we impose, where we remove all the ice shelves to kind of get to this upper bound of sea level. And so that's captured in the box 9.4 of the high-end storyline for the 21st century sea level rise, and talking about this deep uncertainty. So that basically is MIP6 AbuMIP, and those removing of the ice shelves is basically another way to look at modeling due to Nowicki and modeling due to expected stations, and they give similar high numbers. So we know that there's a potential to get to those high numbers, except that we may not be sure about how we actually get those processes in the models. Okay, so now what about beyond 2100? What does the story look like for Antarctica? Because in a way, from the medium confidence processes, all of the ice sheet models, it's not that much sea level. So what we did, and we have a paper right now under review with ISMEP6, is that we extended, because we finally had the climate model runs that were longer, so we could finally answer that question. So we can't do a modeling run until we have the climate forcing. And so we have a paper under review. And so now you can see that actually 2100 was really well behaved. 2300 is really badly behaved and even more deeply uncertain. You can see this whole zoo, basically ice sheet models in those cases where basically you have a lot of ice being lost, is basically where the marine ice sheet instability started to be triggered. You're having this kind of collapse that is kind of happening. Is that it takes time, maybe not under the 100-year time scales. It may take longer for this to happen. Anyway, watch out that paper when it comes out. So let's come back to this uncertainty. We model what we know. And so really the key question that I wanted to get at is that what are those challenges that we need to work as a community? And therefore, why do I think this is an amazing time to start being an ice sheet modeler or to think about this question? So how do we make progress with this deep uncertainty? Well, in the first figure that I put, this is what Antarctica looked like when my grandmother was born. Okay, that map, this is the knowledge that it was in 1905 or 3. Well, we don't have most of Antarctica. I mean, we have the peninsula, we have Wilkes Land. We know that there is a Ross ice shelves, but we don't really have the control of many, many things. We're missing a lot of East Antarctica. So, right, so a knowledge of Antarctica when my grandmother was born was not really, really well known. In contrast, this is a beautiful image of knowledge of Antarctica from Cryosat when my kids were born. Okay, so the message I want you to take is that we model what we know, and I cannot model something that I don't know. How I can model something, I need to be able to observe it first. Okay, so if you take anything up to this point, is that it is incredible, and that's what I find is really exciting, the amount of observations and how the observations have changed and how they're keeping on changing a field. So let's keep digging a bit more into this. We model what we know and model observations. Observations always drive model development. And the super, super cool thing and the super exciting things is that now there is too many observations. They're becoming incredible. And I try to reflect that with a paper that's ice elevation over subglacial lakes in Antarctica. So subglacial lakes in Antarctica, when I started my PhD, they didn't, we think they were pretty stable. We had like Lake Vostok and that was it. The idea that you could have subglacial lakes that were interconnected and that could basically discharge and lower down the ice sheet, that was new, right? This happened when I was doing my PhD, and that was all driven by observations. So before I started my PhD in ISAT, these were the tracks that we would have. So for a given subglacial lake, that's 10 kilometers, this is my bar, you might have basically 4 lines, right? And this is, you would then have to understand the process based on 4 lines. And then you move on to Cryosat 2. And actually, I really wanted to do a PhD using Cryosat. And I said I wanted to be an observationalist. But basically, and my advisor was the project scientist for Cryosat. So I really thought that I was going to do an observational PhD. But then when I met him, he was like, oh, you know, Sophie, I really want you to understand the modeling of transition zone. And so let's do that. So it was a total career change. Like I have a master's in remote sensing, and I really thought I would be a remote sensor, not an ice sheet modeler. But then basically, as a takeaway, this is why I think it's super exciting, this integration between ice sheet models and observations and how they're often connected. Maybe it's also because of my own path. Anyway, so Cryosat 2 is incredible. You start now kind of seeing much more observations over the subglacial lakes. And so you can now start monitoring and how they change really at very, very fine spatial resolution. And now you move to ISAT 2, right? And you have even more grid patterns and more dense lines and more information. What is also pretty cool about this image is that, okay, you now have a long climate record of the ice sheets. So you can also start saying, is the process that I'm seeing in these observations very fine, deeply, and really understanding what's going on? Was there any kind of hint of this in the past when I had not so many observations? So those kind of questions are now becoming possible, and those were not possible until now. That's why I think it's super exciting. Anyway, so observations are becoming increasingly invaluable into our understanding of the ice sheet, and there's still processes that need to be discovered. One of those discoveries, actually, is the Fun Aquifer. That's a very, very new discovery. It was a discovery made by mistake. The reason that we discovered the Fun Aquifer is because with Operation Icebridge, we wanted to divide flight line that would basically capture the bedrock beneath the Greenland ice sheet. And so I was on the science team there. And as a modeler, my role was to kind of say what was the most important thing missing for ice sheet models. And I would say, bedrock, bedrock. I don't know what my bedrock is. I need to know about bedrock because I know therefore how my ice sheet will relax. So this is a known unknown that we know that we need to fix towards getting this deep uncertainty. And so that's why we were trying to kind of fly flight lines that would get towards information of the bed. Unfortunately, when we designed those flight lines, what happened is that we couldn't get to the bed because there was water in the middle. There was water between the ice, beneath the ice sheets, a few layers down, and that basically blocked the signal. So we kind of didn't manage to kind of get to the bed, but there was a discovery that there was a Fun Aquifer, and that was very new. And that's why it's super cool there is still to date, you can still make discoveries based on observations, and often those discoveries would be made by mistake. And so this discovery of the phonographer in 2014, I remember I was in my office and Laura Koenig kind of showed me also at the same time. There was this traverse by Foster et al. They were also digging pits and they were like, there is water underneath the ice sheet. And this is what this movie is. It's actually the first time that you can see water bubbling. And so Laura was kind of like, she stopped me from working. She's like, come and see the water, come and see the water. There's water beneath the ice sheets, not very deep, right? And so that's basically leading to new ways about thinking about how water travels over the ice and through the ice, how water routes, how do you include fern and phonographer in the models. But really those flight lines were not made to map the phonographer, they were made to map the bedrock beneath the ice sheet. So another excitement. Anyway, so despite tremendous progress, knowns and knowns remain. And so what are those known unknowns that we need to work on? Well, there's the obvious suspect. There is things like calving is still really, really hard. There's things like sliding laws. We still don't know because we can't go beneath the ice sheets. This question about basal hydrology and rheology are also super important. The image that I'm showing and that plot from McGregor et al. Is using ice sheet models to understand whether the models agree whether the bed is frozen or not. And so you can see that in red is where all of the models agree that the bed is frozen. Where all agree that the bed is thawed. And then in blue is when the models all agree that the bed is frozen. But there are still lots of regions where there is white, where basically it means that, well, we don't know. It could be frozen, it could be thawed. And there's also many regions that are really not deep red or deep blue, which means that some model thinks that it is the other way that the others think. So this is another part of this deeper certainty. Knowing what the bed is it frozen or thawed, is actually very important because it will control how the ice sheet responds in order to external forcing and climate forcing. So this is why I really believe that using tons of models is actually key in order to make projections, simply because with those kind of examples, models may disagree. So sometime, despite this challenge that the observation give you, this new knowledge that we're getting and these new discoveries, sometimes the other issue is actually how to implement this new knowledge in ice sheet models. So for the subglacial lake drainage, it's a beautiful example, but then you still have to kind of capture the physics and then make it into the large ice sheet models, and that's not trivial. And sometimes we really don't know what caused the observations that we see. And that's really why I think that, you really need to have many models, simulation for under the same conditions or the same experiment. And there is tons of papers. I mean, it's amazing. I wish I had time to read all the time. There's just papers all the time about new discoveries, new experiments, new knowledge, or new uncertain knowledge. So this one is one about how the subglacial hydrology modulates basal sliding response in response to climate forcing. And so really kind of like tying all together. Right, so how are we going to get there and to reduce this deeper certainty? How do we go beyond the known unknown? Well, one way that we can do is basically do tons of simulations. Right, you can do basically tons of simulations for using one ice sheet model. Each asks them to do tons and then do different, ask them to change little things, like change the sliding load, change this parameter, change this and this. So you can ask them to do tons. And then you can score the models and do something that's called calibrated projections, which is after you've done your crazy ensemble of tons of simulation, you basically look at the observations and then give models that have you score the models by how well they do. And models that reproduce the observations, you give them a high score. Models that don't reproduce the observations so well, you give them a lower score. So it sounds simple, but it's actually really hard to generate an experiment that is unbiased for those kind of simulation. And also, it is not trivial to know what it is observation that you should use for calibrated projections. So here I'm using an example of GRACE, where we had the GRACE measures the total mass change, and it becomes a very blocky because GRACE, for the resolution that GRACE uses, it is a very blocky satellite. If you really want to isolate the signal, and so it means that when we did the model weighting, we basically had to aggregate the ice sheet model to the same grid box as we pretended that, we did the same processing for the ice sheet model that we did for the observation. So that basically it would become a grid box. What would GRACE look, what would this simulation look like if it had been seen by GRACE? All right, so trying to kind of put them two and two together. But if you see that already, it's great. So now you can do this and you can see a model with low weight and you can see a model with high weight. The model that has high weight does not have high weight everywhere. And you need to understand why. But the drawback about that is that you're using, okay, GRACE, which is great, but then you're losing a lot of this fine scale information that maybe ISTAT would have given you, or the altimetry. And so it's really, which observation is the right observation is basically a good question. The other question is, it takes a long time to do simulations, and so maybe should we just do emulators the whole way, right? So you do a few ice sheet model runs, and then the rest is that you design this emulator, which is machine learning, and you basically fill the gap that way. And maybe that way, by doing a lot of that, we'll start identifying processes that none of our simulation actually capture, and region that we need to really focus on. Another way to think about the problem, I think that are cool developments, is that because numerical simulation take a really long time, maybe we actually need a whole new type of model, right? And this is really cool areas happening in the glacier modeling community, where they are basically using ice sheet models applied to glacier, and then using machine learning to infer different projections. And so that could be the way forward for our community, the ice sheet modeling community too. What we've learned in the recent past with ISMEP, for example, and what we are learning is that although ice sheet models are much better at capturing the present day, reproducing the historical or the recent past is actually totally something we still can't do as a community. This is probably one of the most infamous plots for ISMEP, because it's not something that we actually, the protocol we told ice sheet models to come to the present day the way that they thought was the best way. So it means that any papers that they would be publishing up to then would basically one of those lines. And you can see that they are all over the place. And then in GRACE, the observations. And so you can see that the majority of ice sheet models do not reproduce the recent past of the observations, and that's maybe problematic. So that's something that we need to work as a community. And therefore, we need to understand, why is that the case? Is it because we don't have the right physics, or is it because of something else? But it comes back to this other question about when you are going to do model observation intercomparison, you need to also think about the question about what is the true uncertainty in observations. Is it really is the uncertainty bigger than actually it could be? And this question about which observations to use, for how long, is it better to use time series, or are you wanting to kind of do spatial patterns? How would you assign weights? So those are questions that are super exciting that we need to work as a community. Even if you could reproduce the historical, if you wanted to, with your favorite ice sheet model, you also need knowledge about the historical climate forcing, and that's super tricky. Here I'm showing the results of Greenland SMB MIP, which kind of looks at just surface mass balance model. And you can see there's basically a spread, just like the ice sheet model. And actually that spread, right, so that big square, this is what the surface mass balance model from SMB MIP, which has nothing to do with ISMIP, how that would plot to ISMIP. I then put it into this blue line on the ISMIP infamous plot. And that spread is pretty much equivalent, right? So for me, this is when you're like, okay, right. The real question that we need to ask as a community right now is, what is really the right surface mass balance forcing? Should I always use regional climate model? Because we think that they are really good because they give us this very fine scale information about the climate forcing, but then different regional climate model give different results. And so therefore, which one should I use? What is the uncertainty in that? How about the different components of surface mass balance? Because when we force ice sheet models, okay, surface mass balance is great because it tells me how much I need to grow and shrink for the atmosphere, but then water runoff and this melt comes into play in some of our parameterizations for the oceans. And so we need to know that too. For calving, we also need to know that. So those are big questions. And also big questions that we're realizing right now is that surface mass balance that are modeled, they actually play a big role in observational product. And so how do we get into that? So really, I think as a community, thinking about how to improve atmospheric and oceanic forcing is something that we really need to do. And this is for now moving on into the future, looking at typical ISMEP6 simulations. One of them is a normal climate model run. The other one is the same climate model run, and then with surface mass balance also calculated with the original climate model. And so the key takeaway message is that the solid lines are the one that you get from the original climate model. The dashed line is the one that you would get from the normal climate model. And so they don't always go the same way, right? Sometimes the dashed line is above. So if you think about the blue line, the dashed line is above the solid line. So, and then if you look at the red line, is the opposite way around. So then what do you do? Like, it's not even clear. It's not always going, it's not even a consistent answer in the same trends, right? So in some cases, what it means is that by using regional climate model, I would be adding more surface mass balance. And then in the other one, I would be adding less in terms of effect. So we really need to kind of think about these ways. How do we better do this kind of forcing? It becomes even harder in terms of long scale projections. Here I'm thinking about how do I go into 2300 projections? Well, I can't do it if there is no climate forcing. And this is something that is a very strong message that we're trying to give the semi-climate models. However, for them, doing 23 runs to 2300 is very expensive. It's not something that's interesting for them. It's not something that they really care about. Unfortunately, it's something that we, ice modelers, need. Because remember, at the beginning of middle of my talk, I had the Antarctica, and all of the models, actually, this ice model projections were pretty kind of close together for the first 2100, and then you go back to 2300, and you have a big spaghetti line that goes all over the place, right? Because basically ice sheet has a long time scale response, and so we need long simulation. And so for those long simulations, we need long climate forcing, and so we really need the climate community to help us with that. So this is the key takeaway message. Coming back to how do we make progress to this uncertainty? Observations, hopefully, I managed to convince you that are really key in helping us understand what I need to model and whether I'm modeling them right. But they're always very hard to understand too, and that's why there's lots of research going there. Like, I mean, why would nearby glacier not behave the same way, right? This is basically different glaciers in Antarctica that are super close to each other, so you can think that they probably feel the same atmosphere because they're too close. They may feel slightly different ocean, but they can't be that much different because again, they're so close, right? So the climate forcing are quite similar. So then why do they behave differently? Like why in the first image, the one that are on top are basically accelerating and thinning, whereas the one at the bottom are slowing down. And then why is it that 5 years later, the reverse happens, right? So the problem is that an ice sheet model is that I'm supposed to kind of capture those kind of understanding, but until I don't know what causes, then I really cannot put into my models. So there's tons of research and the data, there's tons of data to look at those questions. So, okay, so many questions, so little time. And how are we going to make progress? I think the thing that really inspired me, Megan, when you asked me my title, is I was also thinking about there are so many opportunities in this new open age of open science. There are opportunities that were not there when I started. There are aspects like GHub that is trying to make iSheet research accessible either by making data accessible, new type of data, or making tools accessible in Jupyter Notebook, for example. You have CryoCloud, again, that kind of allows collaboration and allow to cloud computing and sharing Jupyter Notebooks. You have things like Q Greenland, and there's one for Antarctica too, GIS packages with tons of information that are free for anyone that's just about to start that they can use. So basically the resources and this knowledge that's out there, you could just basically decide, okay, I'm going to be an iSheet modeler right now and actually go or think about iSheet processing and actually go and have the tools available to you. And of course, there's so many observations that we can learn and that we need to kind of learn and dig into, which could be super awesome because it means that there's discoveries to be made, or which could be super annoying because there's discoveries to be made and I don't know how I'm going to deal with any of those. So that's why sometimes I'm super happy with observations and sometimes I really kind of do not know how I'm going to use them. But so this is why it's an exciting time because it can go either way. There's also in this new age of virtual science and collaborative effort, thanks to things like COVID in a way, this growing community online, right? So you can join Math and Ice on Zoom and learn all about the latest about what people are thinking. So if you are just coming new to this problem about ice heat and sea level, you can catch up and meet a lot of people very, very, very quickly. There are seminars. Of course, it's amazing that Click has this new webinar series, but NASA GIST has one that also looks just simply at sea level. You have the IGS Global Seminar Series. And so when I have new students that are thinking about whether they want to actually do climate research and sea level research, I'll tell them, just go and watch those seminars, learn, see, does it interest you? Which topic interests you the most? So it's really amazing because you can do that in your own time. I do sometimes when I fold socks, like this amount of information that is there for anyone to look at any time that they want is something that is really new in the past recent years. There's an incredible amount also of collaborative effort that anyone can join, which again is super, super new in a community. So IX, the International Association of Cryosphere Science, has working groups. You can just go and click and join. Instant from SCAR is super open. You can just join the mail links and then come and join. IMBY is the equivalent for observations, again, very, very open. And then, of course, all of the MIPS that Click support, Glacier MIP, SMIP 6, CI SMIP, that brings people together. So why do I think that now is a perfect time to work on iSheet and sea level? I really, truly think that it's an amazing time. I wanted to refresh you the knowledge of Antarctica when my grandmother was born versus the knowledge of Antarctica when my kids were born. So basically the amount of information that we have from observation has really transformed the knowledge. With that knowledge and this new information and this tons of observation that we have, we can still make discoveries of new processes. And we need to make them because we need to understand this deep uncertainty that can lead into sea level rise. That's why we really have to work that. And it's super important because in the end, those projections that we make as a community, they do end up going to things like IPCC, which then do end up being triggered and into, for example, the sea level change tool that anyone can download and then use for adaptations. So we as a community have to morally do the best we can do in terms of projections because people are going to use their projections to decide what to do in their future, how they're going to adapt. It is an exciting time, even just for that point of view. On the one hand, there's also those questions too about, for the deep uncertainty, how do you generate more simulations? Do you have to start doing emulators? Do you have to do other type of machine learning capabilities? Do you have to do something different? How do you process all of the observations that we have in order to understand the processes that are missing? So this is one part. And then all in together, what can be learned about those large data sets? So questions we can do now because we have the computing capability that we didn't have before that are free for anyone to use, like GHub or CryoCloud or Q Greenland. And so really it's a time that I think is the opportunities for discoveries and novel methods is really there, and that needs to be done. And so there are challenges, big challenges, including how to improve polar climate and ice sheet models. But we have all at hand to basically reduce this uncertainty in sea level and climate projections. And so with this, I will thank you. And I really have to thank, of course, all of the people that worked in CLIC for supporting. This is the first workshop, by the way, at Goddard, when we had modelers from different countries who couldn't see eye to eye. We were frenemies, and then we became friends a bit later. For our work, we were awarded an IGS medal. But really, in a way, a lot of our drivers are our families. That's why I really need to thank them. And so it is really an exciting time to be doing climate research and sea level research and ice sheet research. And I will stop.
Well, thank you so much. I really love that framing with your grandmother. That was really I feel like you make a really great pitch for working on sea level rise and all these questions. I want to open it up if anybody has any questions for Sophie. I'm curious if you, at this point, if you could have any observations in the whole world, what would you like to have?
Yeah, so right now we really need to target more observations along the margins of the ice sheets. And it needs to be not just ice elevation, it needs to be ice elevation, and it needs to be at the same time ice velocities, and it needs to be at the same time surface temperature. Like you really need to have observing everything that you can in those very, very near band regions, because those are the regions where there is probably processes that we don't know exist yet. So if you think too about how the discovery of freshwater melting on Antarctica, that's still also very, very new, right? And that was done by field work. But we really have to have lots of observations of different type in those regions that are the critical regions, the margins of the ice sheets where a lot of the key triggers can happen. Because once you have something triggered, then you cannot go on.
Great. Anybody have any questions at all? Okay. Well, I want to thank you so much.
It was my pleasure.
All right. We'll let you go. Have a great day.
Bye.